Hello everyone, it's a pleasure to be a part of Asia Pacific Conference on Communications 2021. I am Lokesh here to present our work on biogeography-inspired optimal scheduling for TSAH networks. With the advent of Industrial Internet of Things, the IEEE 802.15.4e time-slotted channel hopping behavioral mode had gained prominence due to its ability to provide low latency, low power and reliable communication. Schedule learning is not the part of standard and is open to implementation. Schedule decides when a node in the network has to transmit or receive data, and hence its design is very important to achieve optimal network performance. We explore the biogeography based optimization techniques to solve the TSAS scheduling problem and propose a new scheduling algorithm. We compare the performance of proposed bias algorithm with the default TSAS scheduling algorithm, namely minimal scheduling function or MSF. The existing scheduling algorithms cannot serve the growing demands of market. Manufacturing process has been revolutionized by the introduction of Industrial Internet of Things. Industrial Internet of Things and wireless sensor networks have been growing enormously in recent times. Due to the mobility of nodes in the network or due to the required reconfigurations, the networks are very dynamic in nature. Hence, the schedule design should be compatible for dynamic networks. The major goals of any schedule design are to construct a conflict-free schedule, minimize delay and energy consumption, and to ensure fairness in the network. The biogeography-based optimization has been proposed by Dan Simon, inspired by the migration, evolution, extinction, and mutation patterns of species in the nature. It has been applied to solve several real-world optimization problems such as supply chain design, hub competitive location, patient admission problem. Now we discuss our network model. We consider a set of nodes n whose routing protocol is given by RPL, which creates a distance-oriented directed acyclic graph tree routing among the nodes in the network. In TSH, time is divided into slots and the available bandwidth is divided into channels. The resource unit for communication is known as cell and is given by the doublet T, K. Let the total number of channels is M, and the group of capital T time slots constitutes a slot frame. Now schedule is a T cross M matrix whose each element is a subset of links in the network. Schedule defines and specifies the cells in a slot frame in which each node should communicate. Schedule is maintained by the border router. In the given sample network, N0 is the border router. It will have a knowledge of entire network topology and the queue length at each node. We show a sample schedule for the given network. We now mathematically formulate the TSAS scheduling problem. Any schedule should obey several constraints to optimize the network performance. In our work, we classify constraints into two types, namely primary and secondary constraints. Primary constraints are the necessary conditions of a schedule. They form feasible region to search for a schedule. Primary constraint PC1 is that no node can transmit or receive on multiple links simultaneously. Second primary constraint PC2 guarantees the half-duplex nature of links by eliminating simultaneous transmission and reception by a node. For example, links N6 to N4 and N4 to N2 are in primary conflict, since these two links require N4 to simultaneously transmit and receive. PC3 says that no two sibling nodes can share a same time slot since their parent node has to receive on multiple links simultaneously. Secondary constraints improve the performance of network. The schedule can be learned fast and can be directed to optimize the network performance by implying penalties for the violation of secondary constraints. Interference constraints aims to minimize the interference in network and hence maximizes the throughput. In the given example network, let nodes N3 and N4 are in interference range of each other and hence can overhear each other. If links N3 to N1 and N6 to N4 are scheduled in the same cell, then node N4 will receive packets from N6 as well as overhears packets from N3, resulting in a packet drop. The fairness constraint ensures fairness in the network by forcing to allocate the number of cells in the schedule proportional to the number of packets waiting at any node. Latency in the network can be minimized by scheduling neighboring nodes in the immediate time slots. For example, once a packet has been served by the link N6 to N4, the packet has to wait until the link N4 to N2 has been scheduled in the slot frame and hence introduce a buffering delay. Objective function or the regret function of a schedule S calculates the penalty incurred by that schedule due to the violation of secondary constraints. FSC1 calculates the total number of packets lost due to interference. Similarly, FSC2 calculates the penalty for violating SC2 as summation of log Qi by Ci, where Qi is the queue length at node I and Ci is the total number of cells allocated for node I in the slot frame. The penalty incurred by violating SC3 is given by summing the average time gap between the cells scheduled for neighboring nodes in the network. The total penalty of schedule S is given by f of s, which is the sum of all the three penalties. We now present the proposed BIOS TSCH scheduling algorithm. We divide our algorithm into two phases, namely initialization phase and improvement phase. In the initialization phase, we randomly generate Rmax number of schedules from the feasible region created by the primary constraints. We then calculate the schedule regret index of all schedules based on the regret function f discussed earlier and sort the candidate set in the increasing order of their SRIs. In the improvement phase, we perform migration and mutation operation on schedules in candidate set, which are discussed later in the next slide. We then recalculate SRIs and sort the candidate set again. Now the schedule with least SRI is the schedule to be implemented in the network. To perform migration operation, we calculate the parameters lambda I and mu I, which are known as the immigration rate and emigration rates respectively, as shown in the formulas. Here, capital I and capital E are the maximum immigration rate and maximum emigration rates respectively. The migration operation shares the features of good solutions to improve the quality of poor solutions. Here, good solutions are the schedules with low SRI and poor solutions are the schedules with high SRI. The migration operation copies the assigned cells of specific nodes from good solutions to the poor ones such that the primary constraints are not violated. This migration occurs based on the immigration and emigration rates discussed earlier. As demonstrated in the algorithm, schedule SI allows the cells allocated to each node to change to a new location with probability lambda I. The new locations of the cells in SI are copied from a schedule Sj, which shares its slot frame with probability μj. In this process, schedules Si and Sj are said to be undergone immigration and emigration respectively. The mutation operation is performed in BIOS TSCH to increase the diversity in the schedule candidates. Diversity is necessary to face the adverse and new situations as the networks are dynamic in nature. Without mutation operation, good quality solutions in the initial candidate set tend to be more dominant than the other solutions and results in premature convergence of solution. When the network dynamics change, the strategy will be a complete failure due to the lack of diversity in the candidate set. Hence, the mutation operation is included in BIOS in spite of slow convergence. In mutation operation, the schedule is randomly shuffled as shown in the algorithm. Mutation relocates the cells allocated to randomly selected nodes in the slot frame, or cells of two randomly selected nodes is swapped among themselves as long as the schedule is feasible. To evaluate the performance of BIOS TSCH algorithm, we have implemented the schedule algorithm using 60ISH simulator. The simulation parameters are given in the top table. Using second table, we compare the performance of BIOS scheduling algorithm and MSF for 4 different simulation models in different aspects. Due to the primary constraints imposed on the search space of scheduling algorithms, BIOS always generate a conflict-free schedule. Hence, the packet losses due to MAC layer conflicts are wholly avoided, achieving 100% packet delivery ratio. The end-to-end delay performance has also been compared between BIOS and MSF. It is observed that the proposed BIOS algorithm totally outperforms MSF in all simulation scenarios. BIOS is able to handle the time-varying traffic efficiently as compared to MSF. Observing first and third rows of table 3, it can be seen that the increase in delay in BIOS is very less compared to that of MSF. In BIOS, the increase in delay due to the mobility of nodes in TSCH network is marginally higher than that in MSF, as observed from the first and second rows or third and fourth rows. Mobility of nodes causes the network topology to change and hence the entire set of primary constraints change in the BIOS problem. Hence the learning of network has to be restarted and as a result delay is increased. However, the absolute value of delay in BIOS TSCH is still better than MSF for all simulation scenarios. Radio duty cycle of BIOS shows that the active time of nodes does not get affected much with the mobility and it depends only on the number of packets it has to transmit or receive. Since there are no conflicts in BIOS, slot frame need not include duplicate cells for retransmission and hence a very low duty cycle can be maintained by BIOS, making the communication energy efficient. We now discuss the convergence performance of BIOS. In figure A, we show the effect of mutation rate on the convergence performance of BIOS in TSCH network where the nodes are not mobile. When the mutation rate is high, new features are explored in the schedule continuously, making the convergence process slow. Hence, the convergence becomes slower with the increase in mutation rate. However, it helps in achieving a better schedule, that is, a schedule with low penalty. We simulated a TSH network with mobile nodes to demonstrate the pronounced effect of mutation on the converged schedule when the network is dynamic, as shown in figure B. It can be seen that the quality of schedule gets improved significantly when the mutation is allowed in the dynamic networks. The improvement in the schedule quality outweighs the slower convergence of higher mutation rate. In this presentation, we have proposed a biogeography-based optimization schedule for the first time to apply to wireless networking algorithms. The proposed schedule design guarantees the conflict-free scheduling, adapts to different traffic patterns and network topologies, and can be configured to suit the application requirements by introducing appropriate secondary constraints. We have evaluated the performance of BIOS TSH using simulations and show that BIOS outperforms the minimal scheduling function. It has been shown through simulations that proposed scheduling algorithm achieves an improvement of 60% in delay performance and up to 40% of energy efficiency compared to MSF. In future, we wish to explore the swarm formation characteristics where every single bird communicates only with few neighboring birds and hence aids us to design better distributed scheduling algorithms. Thank you. We are happy to answer any queries from the audience.